Hello, everybody. Sorry that I'm not there again this week. I really hope to be back as soon as possible and really hope that will be next week. But until then, we have a little bit more to do. So I outlined everything that's going to be coming up this week already in the email you received. And now I am going to deliver the first part of your section point one notes right now. So throughout the course of the year, we talked a lot about integrals and what they mean, and of course, we know that the integral gives us the amount of area under the curve. And the purpose of this section here is to extend that to the area between two curves. So, for some reason, this section takes me back to like 8th grade math, and it reminds me of these problems here where you have essentially like a donut, and you need to find this yellow area. And the way you end up finding that yellow area, of course, is you find the area of the whole circle as if it wasn't missing the middle part, and you subtract out the middle part, and what you're left with is only kind of that ring. And I kind of see it the same way here in this section, because your book has this really nice picture that I stole, and this is what we're trying to find on the left. We're trying to find the area between graph F and graph G. And there's some boundary lines, some endpoints. So the endpoints are here, A and B, and we're trying to find all of the area that's under curve F but above curve G. And the way you do that is you find the area under curve F and you subtract the area under curve G. And when you find all of the area under curve F and you subtract the area under curve G, what you're left with, of course, is this middle part right here. And they also show you the notation that you're writing out when you're doing that. So here's the area for what's under F, here's the area for what's under G, and all the way on the left over there, you see the area for then what's in between. You can find the difference between the functions and integrate that. And that's the big idea. If you understand that, the rest is just technical math stuff, but this is the idea of the section. The correct way to think about what we're doing here, though, is to, again, think about these representative rectangles. And these are rectangles that are in the kind of bounded area we want, that have a really skinny width, delta x, and the height of these rectangles is given by the value of the function f minus the value of the function g, because the value of the function f would be, you know, the whole y value all the way up to the top. The value of the function g is only the y value from here to here. So when we subtract them, we end up with the distance from curve f to curve g. And that's what we want to use for the height of our rectangle, the distance from curve f to curve g. Now you have to imagine an infinite number of these rectangles being packed in here, all of them having a height given by the value on curve f minus the value on curve g, and their widths being as small as possible. So if you can imagine that, imagine filling this picture up with just more and more and more of these representative rectangles. It creates the pink shaded region, it creates the bounded region, and we would know what to do with that mathematically as well. We go down here, we see the process we're using would be the limit as n approaches infinity of this is just the height of those rectangles, and this is just the width of those rectangles. So what we're summing here is the area. So we're summing the area of all of these little representative rectangles all the way through the bounded region. And we already saw this. We saw this back in chapter 4. We saw that this is our integral. This is our definition of an integral. So what we're going to end up doing in this section is just finding the integral of the difference between the functions. So the big idea here, the conclusion, and then we're just going to see some examples of how to use it, is if f and g are continuous on AB and g of x is less than or equal to f of x for all x's in AB, then the area of the region bounded by the graphs of f and g and the lines x equals a and x equals b, those are the vertical boundaries that we had, is given by this integral, the integral from a to b of f of x minus g of x. So what is this part here? G of x has to be less than or equal to f of x. All that is telling us is that f is the curve on top. So that's important to know because that's how we set up our integral. It's always the curve on the top minus the curve on the bottom. We could still do this process if g was on top, but then it would be g of x minus f of x. It's always the upper curve minus the lowest curve, or the top minus the bottom. And that's why this distinction was made right here, because otherwise this integral wouldn't have been correct if g would have been the top curve. So just remember, upper curve minus the lower curve. So our first example is basically going to be the situation that we just saw. So we're going to try to find the area bounded by 4 different curves. Y equals e to the x, y equals x, x equals 0, and x equals 1. Kind of an easy example. And always the first thing you should do is have a look at what the situation is. Sometimes these are non-calculator problems, so you have to be able to make a table of values to graph all of these functions if you don't automatically know what they look like. So e to the x is the curve on top, obviously. Then this is just the curve x. Ooh, wow, that's a terrible x. And here is x equals 0, the vertical line, and x equals 1, a vertical line through 1. So what we know is that we are trying to find this bounded area, this enclosed area. And our idea would be to make a bunch of rectangles, small as skinny as possible. And the process of making all those rectangles ends up just kind of shading this whole area in. So what we're trying to do now is to find this shaded area. And the big idea from the section says that we should just take the integral from our boundaries, 0 to 1, with the top curve minus the bottom curve, and work it out. And this is a real easy problem, right? Because first I would split it up. Instead of trying to do this all as one function, we can split it up and just look at e to the x and x separately. We know the integral of e to the x is e to the x. We have to evaluate that from 0 to 1. And we know the integral of x is x squared over 2. We have to evaluate that from 0 to 1. I couldn't figure out how to get the computer to do that. And when we plug in, we get e to the 1 minus e to the 0. E to the 0 right here is, of course, 1. And here, when I plug in 1, I get a half. When I plug in 0, I get 0. So if I combine these like terms, minus 1 and minus 0.5, I get e minus 1.5. And e, of course, being 2.71828, that would give me the area under f, above g, between the lines x equals 0 and the line x equals 1. You can also do this calculation on the calculator. The way that I like to do it, so that I have less numbers to round and things like that, is just to type in the integral. So not the two functions separately, but the integral as it stands, and kind of create a new function. When you graph that, it's kind of odd because you don't see the two functions anymore. You just have one new function that's always the difference between those two. That's okay. It's a little bit of a contradiction for what you're expecting to see. And then you just integrate that from 0 to 1. So that's the shading here, going from 0 to 1, and we find out our answer. That's the same thing as what we would get whenever we evaluate this. But actually, that's not the answer. I don't know why there's a funny number there. I think I just took the screenshot before I finished the calculation. Okay, so you type in the function that looks like this, and then you just do your, calculate option area under the curve, which I think is number 7 on the TI-84s. Okay, now, interestingly, in most of your examples, or half of your examples at least, there's not going to be those vertical boundary lines given, where we knew that one of our boundaries was x equals 0, and the other one of our boundaries was x equals 1. It won't be given. Instead, we're only given two functions. And in this situation, again, always start by graphing, even if you have to do it by hand. We can see what's happening here. And what's happening here is we don't need the vertical boundaries. We don't need them because these two graphs intersect each other. Whereas in the previous example, they didn't. Right? There wasn't an intersection point or two, so there wasn't automatically a kind of enclosed area. Whereas here, there is going to be intersection points here and here. So there is going to be an enclosed area. And this enclosed area here we would draw our representative rectangles for, and this is the area that we want to calculate. So the first thing you have to do after you've taken a look at this picture is to figure out where those points of intersection are. Without knowing where those points of intersection are, you can't set up your integral properly. So that's the first thing we have to do. Figure out where those points of intersection lie. So the way we do that is just to set the two equations equal to each other. They were here. So setting the two equations equal to each other. And there's a variety of ways you could have done this. I tried to get a 0 on one side. I factored out the common factor, the greatest common factor. And then I used the zero product property and solved that we'd have 2x equals 0 or x minus 1 equals 0. And these would be my two answers. So those represent the x values. So I have one point of intersection when x is 0. I have another point of intersection when x is 1. Just for fun, I figured out what their y values are. It was a good time by plugging in to either one of these functions. And I know that these are the points of intersection. The y values really don't matter in this example. So what we want to do is find the area. We have to determine which curve is on top. That's another really good reason why you should always start by graphing these examples. So you can see which curve is on top. It's the one that has the negative x squared term. So that's the downward opening parabola. So I have to start with that one right here. It's always going to be the top one minus the bottom one. The parentheses can become really important when you have a longer function that's on the bottom, right? Here it wouldn't really matter, but if you had a longer function, a function that contained more pieces here, then it'd be really important that you remember to distribute the negative to each piece when you do your integration. That's the most common mistake people make in working these types of problems. It's just not distributing the negative. So I decided to try to clean this up a little bit before I integrated it. So I combined my like terms, and I even factored out the constant because each term had a 2, so I had less integration work to do. Now at this point I'm integrating, so the integral of x is x squared over 2, the integral, or the antiderivative of x squared is x cubed over 3, and again I have to evaluate this from 0 to 1. That's just the coincidence between the first and the second examples. And when I plug in a 1, I get 1/2 minus 1/3. And when I plug in a 0, I get a 0 minus a 0. That's just a 0. And when you do the math here, that's 3/6 minus 2/6. That's 1/6. And 2 times 1/6 is 2/6, which reduces to 1/3. So the area between these two parabolas, enclosed by their points of intersection, is 1/3 of a unit squared. I hope that's making sense to you. We have one final example. I put a note here because it's super important that you remember that you're always doing the top curve first when you write the integral. Okay, so our final example, I called it which top curve. So the problem says find the area between the curves f of x equals sine of x and g of x equals x cubed minus 2x minus 1. And taking a look, I see this is my scenario. I didn't have vertical boundaries, so I didn't have these vertical lines where I knew I was only going from here to here. So I'm looking here for points of intersection, and I see that there are 3 of them. And they're here. And those 3 points of intersection make 2 different enclosed areas. We have this enclosed area that we're going to have to work to figure out, and we have this enclosed area. Sorry, it's taking me too long. You can get a cookie or something. That just added about 15 minutes to the YouTube loading time. Okay, I hope your cookie was delicious. So here are the 2 areas that we need to find, and in order to be able to find them, we need to figure out exactly where these 3 points of intersection are occurring. So what we need to do is to solve this equation right here. And I would just say good luck to you with that if you don't have a calculator. So we're going to make this a calculator example. So you can get out your calculator and do your intersect feature or use your solver feature. And you find out here are the 3 points of intersection. All the x values for the points of intersection. So now the question becomes, how do we set up the integral now that we know these points of intersection? And I called the example which top curve, and that's because we can see here that the curve that's on top is different for each of the regions that we're looking at. So in region 1, it's a little bit hard now that I colored it, but in region 1, you can see that our cubic equation, whoa, not what I wanted. In region 1, you can see that our cubic equation is on top, but that cubic equation is on the bottom in the second region. So the other function here is our sine function. It should be clear to you, but I'll just draw it in. Our sine function is on the bottom in the first region, but on the top in the second region. And there's no other way to handle that situation than to just set up two different integrals and add their two results together. So when we're working for the region on the left where the cubic equation is on top, I'm going from this leftmost point of intersection, negative 1.413, to this rightmost point of intersection, so I'm stopping here, and that's negative 0.350. So I'm taking the cubic equation minus the sine function when I'm calculating that left area. And now when I'm setting up an integral to find the area between the curves on the right, I have to switch that. So this time I'm going from negative 0.35, that's here, all the way to here, that's 1.767, and I'm putting the sine curve first and the cubic equation curve second because the sine curve is on the top. This is an integral you can evaluate by hand, no problem, but I said already this was going to be our calculator example, so we can make it our calculator example. So I again did my method of combining the curves in the calculator. So here's the cubic minus the sine curve, and I get a new curve that doesn't resemble what we have, but I just need to know what is the area under this curve from negative 1.413 to negative 0.350, and when I perform that calculation, this is my area for the region on the left. And then here I switched it, my s got blacked out, but I'm doing the sine curve first minus the cubic function, and this is really important here, this parenthesis. That's what I was trying to say earlier. It also stops on the backside. You have to put that second function in parentheses or distribute the negative yourself if you want this to work out okay. And this I did from negative 0.350 to 1.767, and it gave me this area answer. And what I have to do is add these two results together. So 0.6 basically plus 3.817 gives us 4.418 for our final answer to this problem. So you had three examples. The first one where we had the vertical boundaries given. That tells you already what your limits of integration are going to be. You do your second example with just one region. You find your points of intersection yourself, so you know the boundaries of your limits of integration, and you perform the integration. And the most complicated example here was when we have multiple regions. We have to check to make sure that which curve's on top, so we can set up multiple integrals if needed in order to calculate our final answer. Your homework assignment is due on Friday. It is this long list of problems. There's still a little bit more to come. I'd say we've covered somewhere between 2/3 and 3/4 of section 7.1 in this video, but a wrinkle is coming up in the next video for tomorrow. So you might want to wait, but certainly I would say 75% of these problems you can do right now. The ones that are going to be tricky for you are right now are these ones, I think, and 17. But most of the others should be okay. Okay, I hope that made sense to you, and I hope you enjoyed it. See you tomorrow.